All right, hello and welcome. Every single day, we're navigating a world that's just full of uncertainty. Is it going to rain today? What are the chances my team actually wins the big game? Well, probability is this incredible tool we use to make sense of all that uncertainty. It's really the language of chance, and in this explainer, we're going to learn how to speak it.
And I love this because really everything in probability lives on this super simple scale. On one end, you've got 0. That means an event is totally, completely impossible. On the other end, you've got 1. That means the event is absolutely certain to happen. Everything else, literally every other possibility, is just a number somewhere between 0 and 1.
So let's take an example. If a survey tells you the probability of someone believing they've seen a ghost is 0.183, what does that number really mean? It's not just some random decimal. It's a precise measurement. Figuring out how we get to that number and what it lets us do is exactly what we're going to cover.
And here's how we're going to do it. First, we'll get the basic vocabulary down with the language of chance. Then, we'll jump into calculating the chances. After that, we'll see how it all works with probability in the real world. And finally, we'll learn how to interpret it all in significance and the odds.
Okay, let's start at the beginning. Before we can start calculating anything, we have to be on the same page about the words we're using. This is the fundamental language of chance.
First up is the word event. Now, it sounds simple, right? But in probability, it's very specific. An event is just any collection of outcomes you get from some kind of procedure. So, for example, if the procedure is flipping a coin 3 times, an event could be something like getting at least 1 head.
Now, let's get even more specific with a simple event. This is an outcome that you absolutely cannot break down any further. So if you roll 1 die, getting a 5 is a simple event. But what about rolling an even number? Nope, that is not a simple event because you can break it down into 3 simpler events: rolling a 2, a 4, or a 6.
So where do all these simple events live? Well, they live in something called the sample space. The easiest way to think about it is that the sample space is the complete universe of every single possible simple event. It is the master list of everything that could possibly happen.
And this slide right here is fantastic because it just ties all those definitions together. Take a look. Our procedure is observing 3 births. The sample space on the right is the complete list of all 8 possible outcomes. And our event, 2 boys and 1 girl, isn't just one thing. It's actually a collection of 3 different simple events from that sample space. See how that all fits together?
Okay, now that we're all speaking the same language, we can get to the really fun part, the calculations. Let's look at the 3 main ways we can actually figure out the probability of an event.
We've got 3 main tools in our toolbox. First is relative frequency, which is all about observation, just counting what actually happens. Then you've got the classical approach, which is perfect for things like dice and cards, where every outcome is equally likely. And finally, there's subjective probability, which is basically an educated guess based on your knowledge.
So, let's dig into relative frequency. This is probability based on what we see in the real world. You just run a procedure, or watch it happen again and again, and you count how many times your event happens. The probability is just the number of times it happened, divided by the total number of times you tried. This is exactly how we'd figure out the probability of an airline crash, by looking at past data.
Now, the classical approach is a bit more theoretical. It's perfect for those clean situations where every outcome has the exact same chance of happening, like a fair coin flip or a roll of the dice. With this method, you don't even have to run an experiment. You just divide the number of ways your event can happen by the total number of possible outcomes.
All right, enough with the theory. Let's see how this stuff actually works in the real world. We're going to take these ideas and apply them right back to that ghost question from the beginning.
So here's our setup, and this comes from a real survey by the Pew Research Center. A group of adults were asked a really straightforward question: have you ever been in the presence of a ghost? This is just a classic scenario for a probability problem based on observed data.
And here are the results. Out of 2,003 people who answered, 366 said yes, and 1,637 said no. I mean, the chart makes it obvious that most people said no, but that's still a pretty significant chunk of people who said yes. These are the raw numbers we're going to work with.
So which of our approaches do we use? Well, this is all based on observed survey data, so we're going to use the relative frequency method. We take the number of people who said yes, that's 366, and we divide it by the total number of people they asked, 2,003. And there it is, 0.183. So what does that number mean?
It means, based on this survey, there's an 18.3% chance that a randomly picked adult would say they've seen a ghost. You know, getting the number is only half the battle. In this last section, we're going to talk about how we use these numbers to make judgments, to decide if something is statistically significant, and to really understand the difference between true probability and the odds you might see at a casino.
Okay, this next idea is huge. The rare event rule is a cornerstone of statistics. It basically says this: if you make an assumption and then you see something happen that is super unlikely based on that assumption, then your original assumption was probably wrong. This is the core logic behind how we test scientific ideas.
Now let's talk about odds, because they aren't always the same thing as probability. This roulette example is perfect. Your actual probability of winning a bet on a single number is 1 in 38. But the casino says they'll pay you 35 to 1. So, wait a minute. What happened to the other two numbers? Where's that difference coming from?
And this slide just lays it all out plain and simple. This is the house edge. The actual odds against you are 37 to 1. There are 37 ways for you to lose and only one way to win. A totally fair game would pay you 37 times your bet, but the casino's payoff odds are only 35 to 1. That little 2-unit difference is their built-in profit, and it's how they always win in the long run.
And that really brings us to our final most important question. Probability is all around us, but it's so important to ask what those numbers really mean. Are you being told the actual probability of something happening, or are you just being told the price to play the game? That's a question worth asking.